right, so let's take a quick review about the material properties. So in section 4.5, we will look into a few cases, a few categories, and summarize the material property. So the first case is the simplest one, that is the perfect dielectric, which has zero conductivity, which suggests that there is no attenuation for wave propagating in perfect dielectric. So alpha equals to 0, and beta, the phase constant, is omega times square root of mu times epsilon. So the good thing about wave in perfect dielectric is that there is no attenuation. The propagation constant gamma is a purely imaginary number. So there alpha equals to 0, beta is non-zero, and can be expressed as, so everything goes well, like what we have in vacuum space. And the eta, the intrinsic impedance, is a pure real number as well, which is simple and beautiful, right? Okay, I see. So the wave propagates without attenuation, and the E and H field are in phase. Because eta is a real number, all right? And here are some alternative representation for the basic parameters for the EM wave. So you can see that you can use relative permeability and relative permittivity to characterize these properties. And the second category is imperfect dielectric, right? And this one is particularly useful because most non-conductive material falls into this category, all right? So most natural material has a small conductivity, but this is not a large number. So they are referred to as imperfect dielectric. Sigma is non-zero, but it's not a large number. So as a consequence, even though that we know that if you have a non-zero sigma, then all the expression for propagation constant, phase velocity, intrinsic impedance becomes much more complicated. Nevertheless, as long as the assumption of small conductivity is valid, then this expression can be much simplified, right? So because the loss tangent is small, that is sigma over omega epsilon is much smaller than 1, then the expression, for example, the propagation constant, can be simplified. The most useful tool that we will use here is binomial expansion. 这叫什么？二项式展开，对不对 ？Binomial expansion。对了，二项式展开。So 1 plus x to the n to the order n, if x is a small number. No. In this expansion, x doesn't have to be a small number, okay? So just using the binomial expansion, 1 plus x to the n's is 1 plus nx times n minus 1 over 2 gamma 2. This is a gamma function, okay? 连乘的 gamma function. X to the square, and you can express for x to the third, x to the fourth, things like that. So using the binomial expansion, the expression for the propagation constant can be modified as this, which this is can be expressed as this. And we already know that sigma over omega epsilon is much smaller than 1. Then we can use the so-called binomial approximation. Not only the binomial expansion, we will use binomial approximation. But anyway, let's use binomial expansion and taking the first 4 terms of this expression. So we have first term, second term, third term, and fourth term. So you have the first and third term to form the real part, and the second and fourth term to form the imaginary part. And here you can, what you can observe here is this thing is much smaller than 1. This thing, the magnitude of this thing is much smaller than 1, right? So at a certain point, the second term can be neglected. 好了，所以这边我们看到我们这边用的是那个2项式定理取前4项了所以把这个展开之后取了前面的4项，那后面的5、6、7、8项以后的就被丢掉了，所以你会看到这边本来是等号，这边变成是破折号，趋近事实上，假如你能够有这个条件，也就是 sigma over omega epsilon 很小很小的话，那其实后面这2项也可以被丢掉了。其实是可以被丢掉的那假如他们被丢掉，我们这边的这几页就是要跟你讲说，这一项跟这一项可以被丢掉。OK。Alright, so based on the binomial expansion, we express alpha with 2 terms, first 2 terms, beta with the first 2 terms as well. And VP, by definition, is omega over beta, so it can be formed as this. And note that because this is a small number, so we in fact use the so-called binomial approximation. So you can see that it's just taking the minus sign to get this result. And lambda, which is defined as 2 pi over beta, also applies the binomial approximation method, so that it simply flipped the sign over here, because this is a small number. And we can do the same thing for eta, the intrinsic impedance. Here we have only the first 3 terms. So this here is the real part, and this is the imaginary part. So the next thing is to discuss, based on the assumption that the loss tangent is much smaller than 1, what happens with those parameter VP, lambda, and eta. So we would like to see the impact of a small number. So assume that the loss tangent equals to 0.1, which is not really small in most material. 0.1 is not a very small number for our everyday material, solid material. So it's this in fact is not a small number, but for the calculation here it's 0.1. So we see what happened with assuming sigma over omega epsilon equals to 0.1. And the consequence is the third part over here, this one and this one are, this one is 1 over 800. This one is 3 over 800. So it's much smaller, much smaller. And the imaginary part of the first one over here, like this one. This one is, this one, alpha. Is 1 over 20, which is, so comparing the 3 number, 1 over 20, 1 over 800, 3 over 800, I guess we can confidently neglect 1 over 800, 3 over 800, and 1 over 20, we should have this term, all right? So what is the consequence? For all practical purposes, the only significant feature different from the perfect dielectric case is that only the attenuation should account for the non-zero conductivity, For the calculation of beta, VP, and lambda, you can just assume sigma equals to 0, you can neglect the term. But the attenuation cannot be neglected, while the other terms can be neglected. Okay, so here is the very last case, good conductor, which means the sigma over omega epsilon is much, much greater than 1. And the result is alpha is about the same as beta, which is the case we have seen in example 4.6 for seawater. So the VP is, you need to account for sigma as well as the lambda for the 2 cases. For the velocity and the wavelength, you need to account for the loss tangent. And so is the eta, the intrinsic impedance. And eta is, and as you can see here, the angle of eta is 45 degrees, as we have seen for the case of seawater. And you will have important parameter called the skin depth. I'm sorry that I'm a little bit late in this case. So I guess I will continue for the discussion about skin depth on Thursday. All right? OK， 那因为时间关系，我们今天就没有 Rubio 了哈，不好意思。